Okay, I kindly greet you at the seventh one-word webinar organized by YoungStatS on the topic of novel advances to maximum likelihood, algebraic approaches to maximum likelihood estimation. YoungStatS is a project taking part in the framework of Young Statisticians Europe initiative of FAINSTATS, supported by the Bernoulli Society for Mathematical Statistics and Probability and the Institute of Mathematical Statistics, IMS, to whom we thank for their support. Today's topic is about MLE, about maximum likelihood estimation, and about algebraic statistics. So in recent decades, algebraic and combinatorial tools have proved useful for computing MLEs and understanding the geometry of the MLE problem, which in recent years led to new and interesting results in combinatorics and algebraic geometry. Today, we have with us three, I would say, very active and leading speakers in the area. Jane Ivy Coons of St. John's College, University of Oxford, United Kingdom, Aida Maraj, University of Michigan and Arbor, USA, and Anna Seigal, Harvard University, USA. I hope I pronounced all the names well. And we have a discussant, Carlos Améndola, a very active personality in the field of Technical University of Munich, who will comment the presentations after their taking place. So without further ado, I give the floor now to Jane Ivy Coons with her presentation. Thank you. Please, Jane.
Yes, hello. Let me just share my screen. All right, how does that look? Good?
Great. It's great.
Yes, okay, so first of all, I'd like to say thank you so much to the organizers for inviting me to come speak today. It's really exciting. It's great to be here. So today I'll be talking about a type of statistical model called Quasiindependence Model, and when they have rational maximum likelihood estimates. And this is a project that I worked on with my PhD supervisor, Seth Sullivan. Okay, so first let's talk about quasi-independence models and what these are. So we'll take x and y as two discrete random variables with state spaces 1 through m and 1 through n respectively. And quasi-independence is a situation in which some combinations of states of x and y cannot occur together, but otherwise they're independent. And so in order to specify a quasi-independence model, we'll fix some set S in M cross N, and these will be the set of states that can occur together. And then the quasi-independence model is parameterized as follows. So it's the set of all probability distributions in the closure of the image of this map, what we'll call phi sub S, goes from R to M plus N to R to the S, and to get the ij component of the image, I take a parameter alpha I times beta j. So the alpha i's are from the m part of this, and the beta j's are from the n part. And so they're multiplied together, which kind of tells us about this independence constraint. Okay, so in particular, this is a monomial map, which means that this quasi-independence model is what we'd call a log linear or a toric model. And just something to note as a sanity check is that if S is all ordered pairs in M cross N, then this is exactly the full two-way independence model. If you just take the probability of I times the probability of Y equals J. So where do these show up? Here are just a couple of examples of studies that have used these. So they've been used to study the social psychology of decision making in some criminal cases. They've also been used to model system failures at nuclear plants, so pretty important, I'd say. And if you'd like to know about their Markov bases, these are discussed in quite a detailed way in this book on Markov bases. Okay, so let's look at a quick example. If this is my set S, and my states are 1 through 3 and 1 through 3, then I can visualize this set using a matrix with entries with rows in 1 through m, and columns in 1 through n, and the ij entry gets a star if ij is in my set and 0 otherwise. So this is just a convenient way to look at these matrices, or to look at these sets. And then if I want to write down the integer matrix that defines this monomial map, well, I get 3 parameters for my first random variable and 3 parameters for my second random variable. And so, for example, this first column corresponds to 1, 1. I get alpha 1 times beta 1. In particular, this matrix includes the row and column marginals of S. I can also define a bipartite graph on this set. So the partite sets are 1 through m and 1 through n. And I let ij be an edge in this graph if and only if ij is in my set. So for this example, I have this bipartite graph with blue squares and purple circles. And so, for example, 1, 2 is an element of my set. And so the edge 1, 2 is present. Okay, so a key property of these bipartite graphs that we'll be interested in is when they're doubly chordal bipartite. And what this means is that every cycle in my bipartite graph of length greater than or equal to 6 has at least 2 chords. And an equivalent characterization is that G does not have a cycle of length greater than or equal to 6, or what we call a double square graph as an induced subgraph. And a double square graph is exactly what it sounds like. It's 2 squares joined along an edge. So this would be a cycle of length 6 that only has 1 chord. And this is what its matrix would look like. So these are the forbidden induced subgraphs for a doubly chordal bipartite graph. Okay, now let's talk a little bit about maximum likelihood estimation. So I'll have U be a matrix of independent identically distributed counts. And I want it to fit with my model. So I want that Uij is equal to 0 for every ij that is not in this set S. The likelihood function for U under this model then is this function that we'll call L of P given U. And so this is the product over all pairs ij in my set of Pij to the Uij. And this looks suspiciously like what I would get if I was given a distribution in my model and I wanted to find the probability of observing this data, except the difference is that here U is fixed and we let P vary over the model. So P is our variable here. And then the maximum likelihood estimate, or MLE, for P given this data is just the maximizer of this likelihood function over the model. So in other words, we can think of this as the distribution in the model that maximizes the probability of observing U. Okay, how can we compute this thing? So in the case of log linear models, a lot of us in the algebraic statistics community like to use what we call Birchs Theorem. And I'll state it in this particular case. First, I'll introduce a little bit of notation. So I'll let Ui plus be the sum where I fix I and let j range over n for ij in my set. So in other words, this is the ith row marginal of my data. Similarly, I'll let U plus j be the jth column marginal of the data. And finally, U plus plus will be the sum of all of the entries of my data. What Birchs theorem says about quasi-independence models is that the MLE is the unique solution, if it exists, to these equations. So first of all, I want my solution p hat to lie in the model, of course. And then I need that the row marginals of my distribution are equal to the normalized row marginals of the data, and that the column marginals of the distribution are equal to the normalized column marginals of the data. And for general log linear models, what this says is that the MLE is the unique distribution that has the same sufficient statistics as my normalized data. Okay, and I said in the beginning of the talk that I particularly care about when we have rational maximum likelihood estimates. So I'll let H denote all of the distributions, or sorry, every P in C to the S in this space where either the sum of the coordinates is equal to 0 or one of the coordinates outside of these hyperplanes for generic data, and we count these critical points with multiplicity. And then we say that our model has rational maximum likelihood estimate if for generic data, the MLE can be written as a rational function in the entries of the data. And in this case, the ML degree of the model is equal to 1. So I'm interested in when I can write this MLE as a rational function in the data and what that rational function is. And so now I can finally state the main theorem of our paper. And this is that any quasi-independence model has rational maximum likelihood estimate if and only if its associated graph is doubly chordal bipartite. I'll talk a little bit about the proof now. So the forward direction, we prove using some polyhedral geometry. So we prove a general result regarding facial submodels of models with rational MLE. And in the backwards direction, we give an explicit formula for the MLE using the clique structures in the graph. Okay, so I'll talk a little bit about these facial submodels. So I'll fix an integer matrix A, and I'll let M sub A be the log linear model that's parameterized by the monomial map that A defines. And I'll let P sub A be the polytope that I get by taking the convex hull of the columns of A. And then I'll fix a matrix B that I get just by selecting some of the columns of A. So its columns are a subset of those of A. Then we say that the log linear model associated to B is a facial submodel of M sub A if the polytope that I get when I take the convex hull of the columns of B is a face of that of A. It's facial submodel. And then what we proved is that if M sub A is a log linear model with rational MLE, and M sub B is a facial submodel of it, then M sub B also needs to have rational MLE. And this is useful to provide obstructions to having rational MLE, because if I can find a facial submodel with higher ML degree, then that means the whole model needs to have higher ML degree. Okay, so how do we prove this? Or how can we use this in the case of quasi-independence models? Well, we look at these forbidden induced subgraphs. So if we have a cycle of length 2k, then the ML degree of that model is k if k is odd, and k minus 1 if it's even. So in particular, this is greater than 1 when k is greater than or equal to 3. And for the double square graph, the ML degree is 2. And so the last kind of component of this is that the columns of your matrix that correspond to an induced subgraph always give you a facial submodel. So if you have one of these things as an induced subgraph and you're not doubly chordal bipartite, then in particular, you can't have rational MLE. Okay, now let's talk about the formula for the rational MLE in the case when you do have a doubly chordal bipartite graph. So first I'll define some clique structures in my graph. So a clique in this set S is going to be any set of the form A cross B for A contained in M and B contained in N. The whole thing needs to be contained in your set S. And so why do we call this a clique? Well, these correspond to complete bipartite subgraphs of your bipartite graph. And then to each ij in my set S, I can associate two sets of cliques. So first of all, max of ij is going to be the set of all containment maximal cliques in S that contain ij. So that's not so bad. The next one is a bit complicated. So I'll let int of ij be the set of all containment maximal intersections of maximal cliques that contain ij. And we will do an example of this. So we'll go back to this example we had before. The three maximal cliques are this top row. So this is 1 cross 1, 2, 3. Right? Then this upper square. This is 1, 2 cross 1, 2. And finally, this column, 1, 2, 3 cross 1. So max of 1, 1. Well, 1, 1 is contained in all of these. So this is all three of these cliques. Int of 1, 1. So these are all of the containment maximal intersections of maximal cliques. So C1 and C2 intersect in 1, 1 and 1, 2. And C2 and C3 intersect in 1, 1, 2, 1. But C1 intersects C3 is not in this because it's just 1, 1, and it's contained in the other ones. So that's kind of how you build these sets. So now we can actually state the theorem. So we'll fix our data matrix U and introduce a little bit of notation. So for any clique, we'll let C plus be the sum over all of the entries of our data for ij in the clique. And so what we showed is that if your set S is such that its bipartite graph is doubly chordal bipartite, then its MLE is rational, and in particular, it has this form. So to look at the ij entry of it, I take the ith row marginal times the jth column marginal, and then I take the product over the sum of all C in this intersection set into ij. So that's my numerator, and the denominator is the sum over all of the data times the product of the sum over the entries in each maximal clique containing ij. Okay, so how can we prove this? So first of all, we need to show that this lies in the model, but we know what the Markov bases of these models look like, so we can plug this MLE into the known generating sets for this ideal and show that p hat does indeed lie in the Zariski closure of the model. And then to prove that the row and column marginals match, we define a poset on the set of maximal cliques that intersect a fixed column. And then we inductively sum the entries of that column to compute the column marginal. And then kind of once you get to the top of the poset, you've shown that the sum of these entries evaluates to the correct column marginal. Okay, so here's a quick example, going back to the set S that we had before. So here's my data. If I look at the 2, 1 entry, the maximal cliques that contain it are this upper square and the first column, and the intersection set is just the intersection of those two. So to get the 2, 1 entry of the MLE, I take the second row marginal, so U2 plus times U plus 1, then times the sum of the entries in this one intersection set, and then P2, and then for the denominator, we get the sum of all of the data times the sums over each of these maximal cliques. So some current and future work on this with Michael Ruddy and Carlotta Langer. We're working on finding parameterizations of these for which the iterative proportional scaling algorithm converges in a single cycle. And when you can do this for higher, so what would be like K-way quasi-independence models. And for some future things that I think would be interesting in this area, first of all, like true or false, if M sub B is a facial submodel of M sub A, then the ML degree of M sub B is less than or equal to that of M sub A. So what we did for the rational MLE case is like maybe the first case of this. Personally, I think it's true, but I don't know why, so this would be an interesting thing to think about. And then of course one could define K-way quasi-independence models, for any K, so you'd have like a tensor instead of just a matrix. And then what are some necessary and sufficient criteria for these to have rational MLE? And I'd like to finish by saying thank you very much to the webinar organizers and to all of you for coming to listen. And I'll end with some references. Thank you very much.
Thank you. Thanks a lot. Virtual clap, naturally. Is there any question? I don't see any in the chat. I will just start with one question and then probably we move to Aida. It's a general one, probably for the general public. Are the ML degrees and the rational MLE estimator, in this case, computed by an exact formula or iteratively? Does this depend on case by case, or does this make sense?
Yeah, I think for, if you have kind of any old model and you don't have a formula for the MLE, then you might use an algorithm like this iterative proportional scaling. And so then that would be computed iteratively. But if you wanted to compute it exactly, then kind of one would need to go through this process for whatever type of model you have and show that it satisfies the right sufficient statistics and things like that. Does that answer your question?
Yes, sure. Thanks a lot. Okay, also in the interest of time, again, thank you for a great presentation. I give the floor now to Aida Maraj. Thanks.
Hello, can you see my slides? Okay.
Yes, yeah.
Okay. First, thank you very much to Andrei and Carlos for inviting me. So I will talk about, the title is A Tale of Two Phylogenetic Models. So the main storyline is given a phylogenetic tree, I will introduce two very different phylogenetic models, and we will ask the question that has connected all us together here about their maximum likelihood estimate. Okay, so this is based on a paper with titled Reciprocal Maximum Likelihood Degrees of Brownian Motion Tree Models, worked with Tobias, Jane, that just gave the first talk, and Chris and Frank. So as I said, so we will, given the phylogenetic or evolutionary tree, we will talk about two models associated to this tree, and we will talk about the phylogenetic toric model, and we will try to compute a formula for the maximum likelihood degree of these models, and then about a Gaussian model associated to this tree called Brownian motion tree model, and we will try to find a formula for the reciprocal maximum likelihood degree of them. So what is an evolutionary tree? Evolutionary trees or phylogenetic trees are used to record the evolution of species in time. They can be represented or realized by rooted directed trees. Here is such a tree. The root always will be one of the leaves, and the direction of edges will be toward leaving that root. So here, because this is a tree, I can also, I have named all the vertices 1 through 0, through 5, and edges also 1 through 5. And each vertex represents species. The vertices in the leaves represent final species, so species that we have data on, and internal vertices represent common ancestors of these species. For instance, species 1 and 2 have the species 4 as their least common ancestor, and so on. So as I said, we will associate to such a tree two very different statistical models. So the first model will be a log linear model, which Jane talked about in her talk. So recall delta n-1 in general is the probability simplex. So delta 5 is all the points in R6 such that the sum of coordinates is 1 and each coordinate is non-negative. Now for the sake of writing later on writing the kind of the rule of the model easier, we are indexing the coordinates of these points with ij, where so pij, where ij's are any two distinct leaves of the tree. So here we have, since the leaves are 0, 1, 2, and 3, we have p01, p02, and so on till to p23. And so the model associated to this tree will be all the points pij in R to the 6 that satisfy this binomial relation intersected with the simplex itself. So the model in this case is the intersection of a toric variety with the simplex. I will soon also give the exact way how we get this model, but for now, just I'm trying to give a sense of the two different models. On the other side, we can associate this Gaussian model, which is denoted as Brownian motion tree model, which is the set of all multivariate Gaussian distributions with mean 0 and covariance metrics in this set B of T, where the set B of T are all the matrices that look like this, in this form, intersected with a positive definite column. So so these are very different. One is discrete and the other is continuous. So let's go more into depth on how we get these models first. So for the phylogenetic toric model, so one way to get the model itself, since this is a toric model, is by giving the vanishing ideal as the kernel of some monomial map. So let's define a matrix associated to our tree. So the matrix AT will have rows that are indexed by edges, so edge 1, edge 2, and so on, edge 5, and columns that are indexed by tuples of leaves, distinct leaves. And we have that the entry k ij, so edge k and tuple ij, is 1 if k is in the path from I to j and 0 otherwise. For instance, we have here 0, 1. So the path from 0 to 1 passes through edge 1, edge 4, and edge 5. So we have a 1 in position 1, 4, and 5. And 0, 2, 0, 2 similarly uses 2, 4, and 5. And we have 1 in those positions and 0 otherwise. And this matrix allows us to form a monomial map with the columns of the matrix. So if A0, 1, and so on, A2, 3 are the columns of AT, we have this monomial map that sends each Pij to the Aij, where, like, for instance, P01 will go to E1 times E4 times E5, and so on. And the kernel of this map will be denoted by IT, and the phylogenetic model that I mentioned earlier on is like the variety formed by this ideal IT without the points where, like, that do not make sense to be a probability. So the question is about the maximum likelihood estimation. So the likelihood function, as like Jane did mention for the log linear models, the likelihood function for some data U under this model MT is the function such P01 in this case in power U01 and so on, P23 in power U23. In this talk, instead of computing the maximum likelihood estimate, we will talk about the maximum likelihood degree. And the definition of the maximum likelihood degree is as follows. We take the function, which here it should have been capital L, sorry. We take the likelihood function, we apply log to it, and then we try to find the number of critical points in this log likelihood function. And this is useful because the place where the maximum is achieved in the likelihood function does not change for the log likelihood function also. And the maximum likelihood degree number is useful because it tells us about the complexity of the problem of finding the maximum likelihood estimate. So if the number is 1, then we know that that's, if the maximum likelihood degree is 1, then we know that only one critical point is the maximum likelihood estimate. But on the other side, if we have more, then that means that the problem is more complicated. Okay, so in this situation, we can use another alternative of this definition introduced by Améndola and co-authors in 2019, that the maximum likelihood degree of a toric model is the number of complex points in the model that satisfy these linear constraints, where AT was like the matrix that we just mentioned, for generic data U counted with multiplicity. And for instance, in the picture that in the first evolutionary tree that I mentioned, one can compute that the number of points in our model that satisfy the linear constraints in this here is it's 1. So we have only one such point. We can say something more. We could say something more in more generality, that we could say that the maximum likelihood degree of a phylogenetic toric tree is a topological invariant. So it depends only on the structure of the tree itself. In particular, it's equal to the product for every internal node of the tree of the 2 to the outer degree of that tree of that node minus outer degree of the node minus 1, where the outer degree of the node is the number or of the vertex is the number of edges leaving that vertex. For instance, let's take like a slightly more complicated tree so we don't have a 1 as a result. So here we have 2 internal nodes, 6 and 7. 6 has 3 edges leaving that node, and 7 has the same situation, so their outer degrees are both 3, and using the formula here we get that the maximum likelihood degree of the model itself is 16. So there are 16 critical points that are like competing to be the maximum likelihood estimate. Okay, so here is a brief idea on like how the proof works. So the proof is it's induction on the number of internal vertices. So in the base case, the base case is when the tree has only one internal node. So the tree looks like a star, like for instance, the last tree here is like a tree with one internal node. So in this case, we showed that the ML degree of the model itself is equal to the degree of the ideal, which is 2 to the n minus 1. And where n is the number of edges leaving that internal node. For the inductive step, then we used the toric fiber products, which were introduced first by Sullivan. And so we showed that one can kind of decompose our ideal as a toric fiber product of ideals of 2 smaller trees. For instance, in this case, the first tree here can be decomposed in the other 2 trees, and the last 2 trees are formed in the following way. Take, for instance, take the edge E6, and then then remove whatever comes after the vertex 6. Then we get the first tree, and the other tree is remove what is like different from 7. So take 7 to be the root of the other tree. And in fact, the ideal of the first one is a toric fiber product of the ideal of the other 2 trees. And then the result by Améndola, Costa, and Cubias they finishes the job, because they show that in the discrete models, if you log linear models, if your ideal is a toric fiber product, then the ML degrees multiply. Okay, so now we go to the next model. So the next one, Brownian motion tree models. So here is like some setup on how we get the model itself. So first, we will describe a linear space of symmetric matrices associated to such a tree. So denote with LCA of ij the least common ancestor for 2 leaves I and j, and we will associate to or assign to each non-root leaf, sorry, each non-root vertex v the parameter tv. So here we have t1, t2, t3, t4, t5, and we take L of t to be the space of sigma of symmetric matrices that is formed as follows. So sigma has, we index the columns and the rows of sigma by the non-root leaves. So we have 1, 2, and 3, 1, 2, and 3. And the entry ij of sigma will be T of LCA of ij. So for instance, T of LCA of 1, 1 is just T1, because the least common ancestor of 1 and 1 itself is 1. But the least common ancestor of 1 and 2 is 4. So in the position 1, 2, we have 4. The least common ancestor of 1 and 5 is 3 is 5. So here we have T5 and so on. So take the set of all such matrices for any choice of these T1, T2, T3, T4, T5. And then the Brownian motion tree model itself for the tree is the set of multivariate Gaussian distributions with mean 0 and covariance matrix sigma that is of this form and that is positive definite. In other words, all the eigenvalues are positive. So in this case, we ask the same question. So we want to end up to the maximum likelihood degree and to this, what I mentioned, the reciprocal maximum likelihood degree. So if we have some sample of data, U1, U2, UK, then the sample covariance matrix is the positive definite matrix S, formed like as a 1 over K and the sum of UI and UI transpose. And the likelihood function is like similarly to the log linear case, is going to be the product of these Gaussian distributions for each of these UIs, and with like some work taking the log of this and doing some simplifications, one can rewrite the log likelihood function in this very nice formula is minus log of determinant of sigma minus trace of S times sigma minus 1. And so the maximum likelihood estimate can be found also by maximizing this new function. And on the other side, one alternative question that can be asked is, instead of taking this function Ls of t, taking this Vs of t, which is log of determinant of sigma minus trace of S inverse times sigma. And this is called the reciprocal log likelihood function, and it stays better on the variety than the first one. And associated similarly to the likelihood degree, we have the reciprocal log likelihood degree, which is the number of complex critical points of our last function in the model counted with multiplicity. And yeah, so in this case, we use an alternative also way of thinking about this number, reciprocal maximum likelihood degree, coming from Sternfels and Euler, where they show that the reciprocal maximum likelihood degree of a linear covariance model in this case is the number of invertible matrices K in the inverse space of LT, such that K minus S minus 1 is in the orthogonal space of LT for fixed generic matrix C. And what we show is that, in fact, the first part it was mostly, almost everything was done by Sternfels, Euler, and Zwernig, but this space L inverse of T happens to be the same as the model, the phylogenetic toric model that I mentioned in the first part. And the perpendicular space L perp of T happens to be the kernel of a T. So in other words, this theorem here with these new observations can be is exactly the definition of the maximum likelihood degree of the phylogenetic toric model that I mentioned earlier. So in other words, in fact, the two models, even though they were very, very different, they happened to have this thing in common, that the reciprocal maximum likelihood degree of the Brownian motion tree model is the same as the maximum likelihood degree of the phylogenetic model that I mentioned earlier. Yes, so and at the very end, so some questions out of this. So the first question is, I did mention this reciprocal maximum likelihood degree. However, the maximum likelihood degree, to my knowledge, is still an open question. There is some work done in the case when there is only one internal node, but however, it's an open question. And associated to this, one thing of interest is also the algebraic degree of the inverse space alpha minus 1 of t. And lastly, so we talked about reciprocal maximum likelihood degree and maximum likelihood degree. What is the connection between these two notions? So also for this, there is, for the last question, there is some partial work done, and in some cases, people have found some connections or some formulas that relate the algebraic degree, the maximum likelihood degree, and the reciprocal maximum likelihood degree. But it would be of interest to have a full classification. And here are some references, and I thank you.
You again, great presentation, virtual clap, actually. Are there any questions? Still none.
Wait.
Yes, please.
Just at the beginning in the phylogenetic toric model, I have maybe a question concerning the an elementary thing. There was mention of complex solutions. I think could it be or complex points for this? Can you say what you mean with the complex? I mean, is it correct? Did
Yes.
I remember correctly that were complex points? And I was
So
wondering whether complex in the elementary sense was meant or something else was meant.
yeah, that's a good question. So even though the models arrive with like, we care only about the real numbers. However, when using algebraic geometry, we like closed fields and nice fields. So I meant complex numbers in like complex numbers, like I plus
In the complex number sense.
A
Okay,
plus I, sorry?
in the usual complex plane
Yeah,
sense.
yeah. Not in like a fancy way. I'm saying this is complex, it's just a complex number
Yeah, okay.
that uses the I such that I squared is -1.
Of course. Yeah, of course. Yeah.
This is to use algebraic geometry or to make use of algebraic geometry.
And in connection with this question, there was also a thing also elementary, how one comes to these equations of the toric variety. I mean, you said two things interact. One is the condition that there has to be a probability measure, and the other is the toric variety. And I did not fully grasp immediately how one comes from the tree to this equation. But yeah, I just say it's as a question, maybe someone asks some other more important question.
No, I missed something for question about, you asked how one comes up with the equations.
Yeah, how one translates the tree to this toric variety equations.
So to my knowledge, I have seen that material first in when people were discussing about, mathematicians were discussing in tropical geometry, where the trees happen very naturally. And I don't know the story how they started thinking about it truthfully. The definition though that I presented here, where is that one? Is slightly, I have seen this more than once happening, like the path that I mentioned. So this is a tree. So for any two leaves, there is a unique path connecting them. So we are associating to every edge of variable. And so it's somehow natural in math to have these definitions. I don't know who came up first, and probably Carlos definitely knows much more than me on this.
Maybe Carlos very shortly, and then we move forward, probably.
Okay.
Yeah, yeah, okay.
Thank you.
Mm-hmm.
Thanks
I think I probably will discuss this during, well, when I talk about the comment about the presentations, and then I think there is more like in the open discussion forum we can.
Okay.
Okay, great. We have a few questions in the chat as well, but we will have, as Carlos said, open discussion at the end with the availability to ask them. So thanks again, Aida, and I give the floor now also to Anna Seigal. Please, I hope you're still with us. Yes, thanks. There are some problems with connections.
I'm still here. Hi, I'm
Great.
just going to share my
Thanks.
screen. Try and share the right thing. All right, can you all see my slides?
Yes.
Thanks a lot to Carlos and Andre for the invitation to speak at the webinar today. It's great to be here, and thanks a lot to Jane and Aida for your great talks so far. So today I'm going to be talking about groups and symmetries in Gaussian graphical models. So firstly, groups and symmetries are quite widely used in various statistical contexts. for example, in the idea of exchangeability, or in the notion of independent and identically distributed, this idea of swapping or permuting different observations or different random variables. And today I'm going to focus on how groups and symmetries can be used to motivate new statistical models, which has also been quite widely studied in the past few decades. And I'll focus on two examples from my own collaborations. So the first is Gaussian group models, which is joint work with Carlos Améndola, Kathleen Cohn, and Philip Reichenbach. And the second is what we call RDAG models, which I'll explain what that is. And that's joint work with Vizu Makam and Philip Reichenbach. And today I'm going to be talking mostly about RDAG models. I'll just mention Gaussian group models briefly at the end, but this project sort of arose as a follow-up to these kinds of ideas in the Gaussian group models paper. And yeah, here are the references at the bottom of the slide here. And throughout the talk, my focus will be on maximum likelihood estimation in these models, so how to estimate parameters, and how to use this group or symmetry structure, which I think of as a sort of algebraic structure of the models to facilitate the finding of the maximum likelihood estimate. All right, and yeah, I'm happy to be interrupted if there's any questions along the way. So I'm going to start by talking about DAG models. So if we have a directed acyclic graph, or a DAG, which I'll call G, with M nodes. So for example, this DAG over here, then we can assign a DAG model to it, which is given by a linear equation, x equals lambda x plus epsilon, where lambda records the weights on the edges that connect these different random variables. So each node xi represents a scalar valued random variable, and the edges say how they relate to each other. So this matrix lambda then has some sparsity pattern. So lambda ij is 0 unless there's an edge from j to I in the graph. And an example of a context in which such models can be used is in causal inference. So there we think of the edge as being the sort of causal impact that the first random variable has on the second, but the edges don't need to be given a causal interpretation. All right, and I'll assume in this talk that this noise term, this epsilon that we have here, is normally distributed with mean 0 and covariance matrix omega, where omega is a diagonal matrix. So what that means in terms of how we're modeling the noise on the different nodes is that the errors are independent from one another. Okay, so in this case, the random vector x, so in this case x1, x2, x3, x4, is a multivariate Gaussian whose mean is 0 and whose concentration, or the inverse of the covariance matrix, has this form. So it can be written in terms of the matrix lambda that gave the weights of how the different variables are related, and a diagonal matrix omega. Okay. So, all right, it's a multivariate Gaussian model. So it has this sort of familiar probability density function, which may be not entirely familiar just because it's parameterized in terms of psi, the inverse of the covariance matrix. So that's why there's a psi inverse appearing here and then a psi appearing here, instead of it being written in terms of the covariance sigma. Okay, and it's mean 0. So this probability density function enables us to see how our mean zero multivariate Gaussian model is just a subset of the positive definite cone. Namely, it's the subset of possible matrices psi that lie in the model. So here's a sort of cartoon picture. So here's the positive definite cone, and then this is the model inside it. So the positive definite cone actually looks a bit more like this, but we'll use a triangle cartoon. So here we have our statistical model of interest, so our particular set of concentration matrices psi, and for example, that set could be the psi that factor in this form that we saw on the previous slide. So they factor in terms of lambda and omega according to this expression here. All right, so now what is an RDAG model? Well, firstly, let's look at an example of DAG. So here we have directed acyclic graph on 3 vertices, and we have edges from 3 to 1 and from 3 to 2. So now our model consists of the concentration matrices that factor like this, where lambda ij is 0, unless there's an edge from j to I in the graph. So what that means is that the matrices lambda and omega look like this. So lambda is mostly 0, but we have 2 non-zero entries in the 1, 3 location, because there's an edge from 3 to 1, and in the 2, 3 location, because there's an edge from 3 to 2. Okay, and then omega gives the variances of our error terms, and this is a diagonal positive definite matrix. So we have these 3 possible diagonal entries, omega 1, omega 2, and omega 3. Okay, so that's our model. We have lambdas that look like this, omegas that look like this, and we plug them into this formula to get its description as a set of concentration matrices. All right. Now an RDAG model is defined on a DAG together with a coloring of its vertices and edges. Okay, so here's an example. It's a similar DAG to the one that we had here, but now each vertex and edge is assigned a color. So vertices 1 and 2 are both blue in this example, and vertex 3 is black, and then both the edges are red. Okay, so this is going to give us a different but somewhat related model to the uncolored DAG model. So what does it look like? Well, if the colors or the edges are the same, then the 2 entries of the lambda matrix have to be the same. So we have that our lambda that gives us the weight of this edge and the lambda that gives us the weight of that edge are the same lambda. And if 2 vertices have the same color, then their variances must be the same. So in this case, our omega has first and second entries equal because vertices 1 and 2 have the same color, and then its third entry is different. Okay, so we can see from this example how introducing the colors into our DAG has taken us from a model with 5 parameters to a model with, let's see, 1, 2, 3 parameters. So adding in the colors to the graph is a way to restrict the DAG model, but still have it be described by some sort of combinatorial description with the colored graph here. Okay, so now for the definition in more generality. So an RDAG model or a restricted DAG model, we fix a DAG, which I'll call G, and now we also fix a coloring, which I'll call C, of its vertices and edges. So for example, we could have this one. Then the RDAG model consists of the concentration matrices that satisfy the following conditions on the matrices lambda and omega. So lambda ij is 0 unless there's an edge from j to I in the graph. So that's the condition that came from the uncolored setting. But now we have some extra conditions that come from the coloring. So lambda ij equals lambda kl. Whenever the edges from j to I and from L to K have the same color. And the diagonal entries of the diagonal matrix omega are equal. So omega I is equal to omega jj whenever vertices I and j have the same color. Okay, so that's the recipe that we use to produce this lambda and this omega corresponding to this model here. That these two are the same because the edges have the same color, and these two are the same because the vertices have the same color. Okay, so how do these models generalize usual DAG models? Well, we can recover the setting of usual DAG models just by giving each vertex and each edge a unique color. We only get extra conditions when we set certain vertices or edges to have the same color. Okay, next question, why do we call them RDAGs? Well, they're inspired by their undirected cousins, which are called RCon models, and are introduced in this paper of Seigal and Lauritsen. And the R stands for restricted, so the colors impose restrictions on the model. Okay, and here's an assumption that we have throughout our study of RDAG models, which is that the coloring is compatible. So what that means is whenever edges j to I and L to K have the same color, this implies that the vertices I and K must have the same color. So for example, compatibility holds here because the edges have the same color. So 1 and 2, the vertices must have the same color, which they do. Okay, so before I've stated any results, an open problem is to extend the results that I will state to the setting where this compatibility condition on the coloring doesn't hold. All right, so now we have our RDAG model, which is a set of concentration matrices in the positive definite cone. And we're looking for the point in the model that's most consistent with some observed data. So here's our setup. We have our positive definite cone, then we have the model, and we have some observed data, and we're looking for the point in the model that's closest to the observed data in some sense. And the sense that we're looking at today is the maximum likelihood estimate. So this is the point in the model that maximizes the likelihood of observing the data. Okay, so we maximize the likelihood function over the model, and there are 4 possibilities for what could happen as we try to do this. So the first is that the likelihood is unbounded from above. The second is that the likelihood is bounded from above, so these are opposites. And then we have 2 strengthenings of the likelihood being bounded from above. The first is that the likelihood is bounded and attains its bound. And then this is the existence of an MLE. And then a possible even better situation that we could hope for is that the MLE doesn't just exist, but exists uniquely. Okay, so here are our 4 possibilities for things that could go well or go badly as we maximize the likelihood function. Okay, so maximum likelihood estimation in RDAG models is linear algebra. So if it's linear algebra, what are the matrices that are involved? Well, we start with our data matrix, Y, where each of the rows corresponds to one of the nodes in our graph, and each one of the columns corresponds to a sample. Okay, so this data matrix may be transposed from the way that you might usually think about a data matrix. The columns are our samples. And from this data matrix Y, we build what we call augmented sample matrices. And we denote these by MYS. So we're going to build one for each vertex color S. Okay, and here's an example. So here's an RDAG model where we have our vertices 3, 4, 5, 6, and 7, all with the same variance, since they have the same color, and they are influencing variables 1 and 2 via this pattern of directed edges with colors. Okay, so we've got a red edge here, we've got some orange ones here, and so on. And what does the augmented sample matrix look like for this example? Well, it's a way to put these rows of this data matrix into this block structured matrix. That's why we call it the augmented sample matrix. So the rows of this matrix, we have one for the vertex color of the 2 child nodes, and then we have some rows for the colors of the edges that connect them. And okay, for example, on the orange row, we have a 0 here because there's no orange edges that connect any of these vertices to number 1. So that explains this 0. And over here, we've got Y3 plus Y5 plus Y6 because there's orange edges that come from 3, 5, and 6. Okay, so to give a definition of the augmented sample matrices in general, it's just some definition according to the adjacency structure of the graph. Okay, and then
may I ask shortly a question there? I understand that you would associate to each node a sequence of data, but what, for example, let's take the augmented matrix and look at the second row there. Then you have Y3. Why would this be Y3? That's what I've not understood. So I just to reformulate, I know how to associate to nodes data, but I would not know how this connects with the edges, or what is associated with the edges.
okay, yes, thanks a lot for your question. Yes, so usually in the usual data matrix, each row corresponds to a node of the graph. So we start with a matrix that in this case has rows Y1 up to Y7. Now we turn this into an augmented sample matrix where some of the rows are indexed by vertices, actually just one, just the top one, and the other rows are indexed by edges. And the way that we put a row of our sample, of our original sample matrix in the row indexed by that edge is to ask, is there an edge of that color coming from that vertex? So for example, for the red edge here, we look at vertex number 1, because this is Y1. It has a single red edge that comes from vertex 3. So that's why this is a Y3. But if we look at vertex 2, there are no red edges that have destination 2. So this is a 0 here. Okay, I hope that answers your question. Be happy to talk about it more.
Yes, for the moment.
Thanks a lot. Thanks for the question. Yeah, so there's, I mean, maybe it's not so important, the detail, but there's some recipe that takes us from a graph here to these potentially quite big matrices. And then I want to argue that maximum likelihood estimation for these models is sort of easy once we've built these matrices. So what do I mean by that? So our log likelihood function, so Aida already mentioned that we can rewrite the log likelihood function in the multivariate Gaussian setting as this expression here, log det of psi minus the trace of psi sy. Okay, this should be a function of psi, where sy is our sample covariance matrix. Okay, and then we construct these augmented sample matrices, okay, one for each vertex color. So here's an example of we saw for what that might look like. And then we can relate the properties of the log likelihood to the properties of these augmented sample matrices. All right, so the log likelihood is unbounded from above if and only if the 0th row of the augmented sample matrix is in the span of the others. Okay, then the log likelihood is bounded from above if and only if the MLE exists. So the MLE exists if and only if the opposite of this first condition holds. Okay, so the 0th row is not in the span of the other rows for all vertex colors S. And the MLE exists uniquely if and only if this matrix has full row rank for each vertex color. Okay, so this result characterizes when the MLE exists and so on, all in terms of various properties of the rows of this matrix. And it also gives us an algorithm to compute the MLE. So how this works is for each vertex color, we project the 0th row of this matrix onto the span of the others to get this projection, which I'll call PYS. Then the maximum likelihood estimates for our lambda entries are the coefficients such that PYS is written as a linear combination of the other rows, so of the other rows of MYS. So that gives us the lambdas, and then the maximum likelihood estimates for the omegas are given by this formula here. So 1 over alpha S times PYS minus MYS0 all squared. So this is just a formula that you can compute. And this alpha S here is just the number of nodes in the graph that have color S. Okay, and I will conclude by just mentioning some connections to Gaussian group models. So here's a question that you could ask, which we were interested in. So here's a here's a set of matrices, a set of M by M matrices. It satisfies the following 3 conditions. So Gij has to be 0 whenever I is not equal to j and there's no edge from j to I in our graph G. Okay, so the set depends on a graph G and a coloring C. Then next, the entries have to be equal whenever there's edges from j to I and from L to K that have the same color. And finally, its diagonal entries have to be equal whenever vertices I and K have the same color. Okay, so this gives us a set of matrices that we obtain from our graph and coloring. And we want to know when it's a group, i.e. when is it the case that if you take the inverse of a matrix in this set, you stay in the set? And when is it the case that when you multiply 2 matrices in this set, you stay in the set? Okay, and we give an answer to this. So the answer is that the graph has to be transitive and it has to satisfy something which we call the butterfly criterion. Okay, but yes, if you explore this question, you may come up with another criterion, which I'd be very happy to hear about. Then, if we fix an RDAG model on a graph G with a coloring C, such that this set of matrices is actually a group, then we have these connections between the various notions of stability that exist in the study of groups, which I won't get into now in the interest of time, and maximum likelihood estimation. So we have that the stability of our matrix Y, whether it's unstable, semi-stable, polystable, or stable, relates to these 4 notions of the likelihood function, whether it's unbounded or bounded, or whether the MLE exists, or whether it exists uniquely. Okay, and in fact, but I won't go into this more now, the theorem holds even when this set of matrices is not a group. Okay, all right, thanks a lot. That's all I wanted to say. Thanks, everyone.
Thank you. Thank you for another excellent presentation. Is there any question? We had one in between already. Maybe then I just give the floor to Carlos, who will have a lot of questions for all you three, and we continue afterwards. Thanks again. Carlos, please.
Okay. So yeah, can everybody hear me, hopefully, and see my screen?
Yes. Yes.
Thank you. Yeah, so first of all, I want to thank the three speakers again for very nice talks and really painting a good picture of what algebraic statistics does in maximum likelihood estimation. And this is really novel, I think. All of these topics are pretty recent, and they explore different facets of ways to look at the statistical models. So I just want to make a few comments and maybe mention some of the topics, highlight some things, and then I will be happy to, well, have some conversation with the speakers. Maybe they want to comment on these points, and then I think we will have the open forum for the audience also to chime in and share their thoughts, and yeah, we'll be happy. I'm looking forward to that. So, okay, so let me then mention, so I already said this is in the context of algebraic statistics, these talks, and I'll just put a link here, that's algebraicstatistics.org. I invite you to visit, and there you will find well, things like the journal of algebraic statistics called Algebraic Statistics Journal, ASTAT, published by MSP. And you will find information about the conference. So there are algebraic statistics conferences happening. Hopefully this one will happen in person next year in Hawaii. So if you're interested, maybe you can check it out. And yeah, so you will find there. We also had some online algebraic statistics seminar that right now it's in pause, but we plan to restart it. So, so you can also visit, and there will be many talks there. Okay, so let me then just mention, so one way of seeing the three talks that we just heard, and this is was very nice. Actually, the order was kind of you know, just by luck that they ended up like this, but then it was perfect because, so Jane started telling us about discrete models, right? In particular, some special log linear models. And this is one of the classical examples where algebraic statistics comes in. And there was a question about toric models. So there's the relationship between toric models and log linear models, which was yeah, very quickly at the beginning of algebraic statistics was found, and then it was exploited, and it was very nice geometry and correspondence between these two. I'll go back to this correspondence a bit later. And then, well, Aida told us about the connection, right? So not only discrete models, but then also connecting to the continuous models. In this case, with the phylogenetic trees, or having these covariance matrices in the Brownian motion tree model, right, which are actually now in the continuous case, where we can think of them as some covariance matrices. And so, yeah, so there is this in between discrete and continuous, and as we saw in Aida's talk, there is a connection between them, right? Maybe unexpected, but now there is a connection there. And then, well, we finished with Anna telling us about more continuous models, in particular some Gaussian models and some specific symmetries. And you could see that all of them had some graphs in a sense, right? So there were some very nice, some doubly bipartite graphs, right, with Jane, and then Aida showed us some nice trees, and Anna had these very nice pictures, right, with the color DAGs. So this is one way of it. We can see there is both discrete and continuous models. Both of them are in the realm of algebraic approaches to maximum likelihood estimation. And so I want to touch on some themes, right, or topics. So one of them is the ML degree. So this was mentioned a few times. And so this maximum likelihood degree, we think of it from the algebraic point of view, we think of it as some algebraic complexity of the maximum likelihood estimation problem. And in particular, it was mentioned that this ML degree is 1 if and only if you can express the MLE, the maximum likelihood estimate, as a rational function of your data. Right? So rational means just a polynomial divided by another polynomial. Right? And in Jane's case, we even had this very nice formula, right, with the cliques of the graph. And yeah, so then it can be higher than 1, right, as Aida told us, and there was already explicit formulas that had to do with the out degrees of the vertices in the tree. And well, I mean, Anna, when she didn't explicitly refer to it, but in this linear algebra approach, so we also have some ways right, to find the MLE, right? And she talked about this algorithm to find it. So yeah, in terms of algebraic complexity, so this is a very nice connection, and maybe there was a question about this, so maybe I'll touch on that. So there is algorithms, right? So we are interested in finding also algorithms to efficiently compute the MLEs. So we care about existence, but then if we know they exist, well, we want to compute them. Right? So that's very important in statistics. And so, we talked about, there was mention of scaling, there was mention of IPS, right? So one classical algorithm that was introduced in the discrete case to find maximum likelihood estimates for log linear models. There was a mention of group actions, there was a mention of projections from the continuous case that Anna talked about. And well, in a sense, so I think one of the questions in the chat, right, was like, what is the relationship between this algebraic complexity and actual, ways to find it, right, efficiently if we want to compute it? And there is, I think, there is a correlation, but it's not completely understood, I would say, in general. So having a high, in terms of writing it out, it's true, right? So if we want to write it as an expression, if we think of it as an algebraic equation that we need to solve the MLE and find the explicit formula, well, so if it's ML degree 1, it's very clear with this rational. If it's ML degree 2, we still have very nice closed form expressions, right? It's a quadratic equation. There was this double square, right? That Jane told us about. She said it was ML degree 2, right? So we can also write down an explicit formula. And of course, when it gets higher, it gets harder. But this doesn't mean that we cannot find it efficiently. Right? So in log linear models, I think in IPS, people use it a lot, and we know there will be, relatively fast convergence, let's say. So we can find it numerically, approximation numerically, but the ML degree may be quite high. And this is another topic. Maybe I'll leave it to the open forum discussion. This difference between the real points and the complex points, because remember the ML degree counts the number of complex critical points to the likelihood function. So one big open area is to study the real points and how these change depending on the data, right? So this is not so clear anymore. And so when do we know that there is a unique solution, positive solution, as in with Birchs Theorem, or when there could be multiple local maxima. And that's where we're more interested in the algebraic approach, because when we want to optimize a likelihood function, and we know there are multiple local maxima, if we do local searches, we're not guaranteed to find the global maximum, right? So that's a big problem, I would say, in many in this situation. This happens a lot in machine learning, for example. And so these algebraic techniques, when we know the ML degree, are very useful, because if we're able to find all the critical points by using algebraic methods, maybe numerical algebraic methods, then we can certify that we will find the global maximum. Right? So there may be many of them, the ML degree may be high, but one can certify. So I think this is one of the best contributions of algebraic statistics to maximum likelihood estimation problem. And okay, the other theme I wanted to talk about was algebraic structures. So this is just a bit more general. We mentioned toric varieties, which are very well studied, very important in algebraic geometry, in discrete geometry. And this corresponding to the log linear models in the statistics. We talked about, well, there was a mention indirectly of LSSMs, which means linear spaces of symmetric matrices. And okay, so there was mention of groups, right? So all of this carries some very nice algebraic structure that is translating to some nice statistical structure. So I guess the theme here, part of the mantra of what's happening, is that these special algebraic and combinatorial properties, as we saw in all three talks, there were some very nice combinatorial properties, translate to some special statistical properties. And I think this is the, the essential part of what's going on in this research, in these directions of exploring algebraic techniques, how they allow us to understand better the statistics, and how the statistics is also inspiring new algebraic approaches, new algebraic things that, so maybe some algebraic geometry would never consider this model, but we know this is coming from statistics, so there is a new new intuition, maybe a new motivation to study this problem. So I guess, yeah, so this is really just the highlights I wanted to give, and then I would like to maybe open the discussion if there are any comments from the speakers on these, or something in general. Thank you.
Thank you. Thanks a lot, Carlos. I give the floor to the three speakers if you would want to respond in any order, but maybe we start with Jane, if you have anything.
I guess I would say so. Just talking about iterative proportional scaling, this IPS algorithm. This is something that I've been thinking about, as I mentioned at the end of my talk. Something to remember with this is that IPS always, at least for log linear models, always outputs a rational function. At each step, you get a rational function of your data. So if you have higher ML degree, it won't converge in finitely many steps to exactly the MLE, and it's very parametrization dependent. So you can have the same model and same log linear model and have two different parametrizations of it. And for one of those, it never gives you the exact rational function. And for the other parameterization that you give it in finitely many steps, it gives you exactly the rational function. And yeah, so that's an interesting question, I think, about which parameterizations of log linear models are like the most friendly for IPS.
Yes, that's a very good point. Also, for people familiar with the graphical models, this IPS, when used even in chordal graphs, where we know that the ML degree is 1, I think there is a theorem that says if you have the right ordering, IPS will converge, in one iteration, right, or 2 iterations, depending on how you count it, you will obtain the answer, right? But it's not true that I think many people, if you find in the literature, they'll say, oh, if it's not the right ordering, then we'll, instead of one time, it will take, you know, twice only. But I think there are counterexamples, right? So even though the ML degree is 1, if you don't have the right ordering when you apply IPS, then you may not obtain this in a finite number of steps. Or I think this is open. I think this may be the question you're studying, right? So
Yeah,
is it true
yeah.
ML degree 1 if and only if you can converge infinitely many steps? I guess.
Yeah, like in fact, you can if you write down a overly complicated parameterization just of like the whole whole probability simplex, you can get that to not converge in ever, like in finite many steps.
Okay.
Yeah. So you can show that it just oscillates kind of back and forth and never really finishes. Yeah, that's all I wanted to say. Thanks, Carlos, for that nice summary.
Okay.
Thanks. Maybe Aida, if anything.
Yeah, thank you, Carlos, for the summary. It was very good. Yeah, and I was gonna point out, thank you for pointing more out the part on the connection between discrete and continuous models in the phylogenetic case. And maybe like the hope may be that there are more connections out there that can help one side or another.
Yes, yeah, I have to say this was a very nice surprise when you found out about this, because I mean, this formula that you managed to prove, right? So with Piotr, we had worked on this when we had this conjecture, and it was like, okay, but it seems like very hard to you know come to how to prove this, right? And in the discrete case, there are like somehow maybe more techniques than in the Gaussian case at this point. But yeah, you managed to find a connection, right, and prove that proving the discrete, you could prove the continuous one. So I think, yeah, this is a very nice story. And the other question that you asked, an open question, is like, okay, you computed the reciprocal ML degree, but what about the ML degree, right? So we also have a formula, right, the conjecture formula. And yeah, so how can one prove this?
But isn't the formula only for the star case?
Oh yes, that's correct. Sorry, yeah, this is we have it for the star case. Yeah. But it's still not proof, right, for the star case. Yeah, this is true. So yeah, how can one extend this to other models? Yeah, so thank you.
Okay, thanks. Maybe also Anna.
Yes, thanks a lot, Carlos, for this summary. I agree that it's very nice to see how some results from the discrete world can help in the Gaussian and vice versa. It'd be nice to develop those connections more. I think it's there's always these two separate worlds of the discrete one or the local linear models and so on, and then this multivariate Gaussian setting. So it's really nice to have situations where they come together and they can help each other. So I think that's really cool. I guess to follow up on a bit the conversation about algorithms and computing the MLEs and whether ML degree is a sort of good notion of how difficult it is to find an MLE. There are some situations, as Carlos and Jane, as you both mentioned, where ML degree 1 gives better convergence, or like convergence in finitely many steps of some algorithm and so on, with an appropriate choice of order. But as far as I'm aware, there's not so much on like convergence if you're ML degree 4 versus ML degree 5, and sort of seeing this ladder of ML degrees as corresponding to sort of difficulty of convergence of corresponding algorithms. But probably or possibly there is something more that can be said there for ML degrees that take values greater than 1, but comparing two values that are both more than 1. But yeah, I don't know if anyone has some thoughts on that, or situations where that type of problem is studied. And then more on the algebraic structures side, and it's something interesting that came up, I think, in all of our talks, was this idea that you have larger model and you're interested in certain submodels of it that are combinatorially defined. So maybe you assign colors to a graph, or you could look at some sort of facial submodels, and you're looking for when nice properties of the larger model translate to the smaller model. And there's ways that you can choose a smaller model well or badly in terms of statistical interpretation, or in terms of how easy it is to compute MLEs and so on. And I think that's a very interesting direction as well, where we can make some choice of which algebraic structures we want to impose, and then look at the statistical implications of that, as well as studying them from a more theoretical perspective.
Yes, I completely agree. Yeah, this is a really good point. Yeah, and I think this is something that is really nice. I mean, it's not that one has to somehow concoct how to find, oh, I want something nice on this side, so what should I find? It's like, it's natural in a sense, right? So like, if you restrict yourself to this very nice symmetric, special combinatoric on one side, then you get something nice on the other side, and vice versa, right? So I think that is very exciting. Yeah.
Thanks. So I would open now the floor to questions. People are leaving, but it's just probably one of the most interesting things, as we discussed at the start. We have a question firstly from Daniel, but I do not think he's still here. It relates to what we have been discussing previously. In general, he wonders whether the maximum likelihood degree is somehow related to how hard it is to find perhaps exactly the ML estimate. I think it was for Jane or Aida, but any three, or Carlos, please just intervene or reply.
Yeah, well, I think somehow we address this, in these comments about like IPS, about like expression, if you want an explicit expression. But I guess, well, one more comment about that would be this algebraic complexity. Can one quantify it in some other complexity terms, right? And maybe in this kind of computer science complexity ideas, right? Or especially in algorithms, right? Okay, so we're thinking in IPS, okay, if it converges finitely many steps or infinitely many steps, or can one do, I think as Anna was saying, right? So like, okay, the ML degree is higher than 1, how bad it is, if it's too large, or like two different models that have ML degree higher than 1, is one really much harder than the other, right, to find the MLE? I think, yeah, this is an interesting question as well.
Carlos and others, and hopefully also others in the public still remaining, will ask questions related to this. How compute, I mean, does algebraic statistics, procedures that you mentioned, and advances related to MLE enable faster computation? Or is the computation even more computationally burdensome?
Well, I think that is a good question. And I would say, well, for me, my first reaction is, well, it depends on the model a lot. Because, okay, one nice thing is that in algebraic geometry, there is all this numerical algebraic geometry that I briefly mentioned, like homotopy continuation and monodromy techniques. I think there was, I don't know if this person is still around. I feel also Jose was in the audience, so he's an expert on this. And yeah, so these techniques are getting better, and they're, I would say, reasonably fast. So this is pretty good. And in the paper that Aida referenced, where we do some just examples where there is IPS, classical IPS compared to homotopy continuation, using the fact that some ML degree is 1, and we are able to beat the classical algorithm by using this algebraic technique. But I don't know, maybe in some other cases it's yeah, I guess it will be harder, right? Or it's not so clear. Like, maybe there is some equivalence thing. Usually, I will say a hard problem, in statistics corresponds somehow to a hard problem in the algebraic side, on the algebraic side. But they can help each other. There's some perspective. Yeah, this will be my first reaction. I don't know, maybe any of you have anything else to add?
There is just please. Yes, Thomas, please.
Just to give my opinion or my impression on this last point, maybe I think, or my impression is just that algebraic complexity would relate to the difficulty in computing, but not necessarily in, numerically computing, this difficulty. So rather more to the computational power, but not necessarily to the statistical difficulty of a problem, because for example, I just using my intuition now. If a density has multiple critical points, then this not necessarily say something about the width of the mass of the probability mass in this distribution. But this latter part would be critical for example, for the accuracy of an estimate. Does this make sense? So I'm coming from statistical perspective. If one aims for the most accurate statistical estimate, then one has to look at the density, at the properties of the density, and yeah, then the concentration of the probability mass is most important. Yeah. So.
Okay. Yeah, I think so. If I understand your comment correctly, so you're saying, okay, maybe not just finding the estimate, which one can do, but maybe like the distribution of this estimator, right? So is this going to have low variance? It's going to have some mean squared error that's reasonable, right? And I don't know, is this in this direction?
Yeah, correct. First of all, the problem itself or the model itself poses a certain density on or gives a certain density, and this already determines how well it is or how good it is possible to determine an estimate. And then, of course, each possible estimator, it has a function of the data points, has again further properties, and exactly what you said, the properties of the estimator then they will depend on the density, but on the properties of the density, but not necessarily by the critical points. But well, that's a bit hand waving, I know, but yeah. But I think that in applications, for example, this accuracy is most important, and therefore I was also asking this question in the chat: is the computational burden actually the critical part, or is it more like that the accuracy should be increased, the accuracy of the estimate?
Yeah. So I think, well, in most of here, the context was, well, trying to find the maximum likelihood estimator, because, okay, we know that this has very nice asymptotic properties, right? In this idea, in this sense, to finding some kind of efficient estimator. But it's true that, especially in the models, in these Brownian motion models that Aida was talking about, maybe the MLE is too costly. And then one looks at this dual MLE. I think this is what she was talking about when talking about the reciprocal ML degree. So it's like studying this dual likelihood and the so-called dual maximum likelihood estimate, which will not be as efficient, but it's usually easier to find. So in these Brownian motion tree models, I think that's in the binary case, when you have this tree, I think this is exactly the case. So you have the dual ML degree is 1, even though the ML degree may be high. So it's very easy to find, computationally speaking, it's easier to find. So instead of solving this big algebraic system, you know there is only one solution. And well, you will not be as efficient as the MLE, but well, asymptotically, it's still pretty good. So I guess then the question would be, okay, trying to look at other estimators, not necessarily the MLE. And then as long as one can study them algebraically, then one could also explore this. So I think that's, yeah, I mean, that would be my thoughts on this. So like,
yeah.
Perhaps another perspective on your question is, if you have an ML degree 1 model and you have this rational formula that expresses the MLE as a function of the input data, then you can hope to see how it changes as you vary your input data. So to give some sort of robustness for the MLE under some changes of the data.
Yeah. I also think that would be the direct statistical target one looks towards, kind of. And if it's always a hope that one, but of course the field might have some other goals in the end. But yeah, I would also say this sensitivity analysis, if this could come out also of the algebraic analysis, that would be very interesting, I guess. Yeah.
Yes. Yeah. Thank you for your comment.
Any other comments?
So we have a question over here. We had some people live watching from the Mathematical Institute here in Oxford. So some questions from the audience now.
Hi, just something really simple and a pretty naive perspective. So I'm normally not in this field of algebraic statistics, but I've been looking into how one can fit manifolds to data. But in this case, the cartoon that Anna suggested earlier suggested that this process of finding maximal likelihood estimation model is a bit like, it's as if like there's a manifold. I mean, there's a manifold of like the possible probability densities, and if there's an observation, you want to kind of find an orthogonal projection to it. Although the real actual picture seems to be more complicated than that, like involving functions and stuff. So was there like, do you think this kind of approach of fitting a projection onto a manifold is realistic? And like whether there has been any like prior research done on this kind of approach? Just like reference request almost. I'm just like an outsider making a simple observation.
Sorry, the lights went off in here, so I'm gonna go try and turn the lights on. I'm really sorry.
Maybe Carlos or
maybe Anna wants to comment on the picture.
I think like everyone in here, I mean, there are two of us here right now, like everyone left, but so that means, you know, she's back.
Sorry, turning the lights back on.
So yeah, that kind of approach, is it viable, and like whether any research was done? Is kind of my question.
Yeah, so thanks a lot for your question. Yeah, so the cartoon picture I showed with this model, sort of looking, as you say, like a one-dimensional manifold, and then this projection onto it. This is what maximum likelihood estimation is, in the sense that you have some model, it's parameterized in some way, and you're projecting, you're finding the point that best fits your data in some sense, which in this case is according to the likelihood function. So it could be like Euclidean distance, and then you'd have some other optimization problem and so on. So I mean, I like to use this cartoon picture because I think that's geometrically what's going on with maximum likelihood estimation. But of course, you can have other models, like your model could consist of a finite set of points, and then you're, just to take an extreme example, then you're projecting, or you're just finding which of the points you're closest to, and so on. So it may not have this nice manifold structure. It also may have singularities. So there's lots of ways in which it might not be a manifold, but the picture of there's some set of interest and you're looking for the closest point on that set, it sort of holds throughout. You also mentioned manifold learning. So I'd say that's more connected to the problem of model selection, where you have some data points, which for you are some points from which you want to infer the manifold that they're on. In the statistical setting, you could think of these points as being your data points, and then you're looking for a model that's good fit to these data points. So that's a case where the model is not already fixed at the outset. Whereas everything we were talking about today, part of the input is that you already have a model that you're looking at.
Yeah, I think that's a good point from Anna, especially. So the models that one can study may have singularities, so then like not a manifold, and that's one of the nice things in algebraic. This algebraic variety, that's what we would like, right? So it's an algebraic variety, but yeah, there may be singularities, and sometimes, especially in model selection, as Anna was saying, these singularities. Things near singularities are very interesting, right? So that's exactly when the nice like hypothesis test of being in the submodel or not becomes relevant in statistics.
I guess
So yeah,
like the low rank matrix, the set of low rank matrices being like a singular space, for example. Yes.
Exactly. That would be an example.
Another thing I might add is just so instead of like orthogonally projecting, we're minimizing the Kullback-Leibler divergence or
right.
AL divergence, but people do think about kind of similar flavor problems with like minimizing like the Euclidean distance to a variety, and then instead of like the ML degree, they have like the Euclidean distance degree, and there's kind of similar.
Oh yeah,
work going on in that world.
Didn't like Professor Sturmfeld do work on that?
Yes. Yeah, so those problems kind of have a similar flavor to that's where you're minimizing different things. Yeah.
So it seems like a sensible idea, although like not necessarily it has been pursued to very explicit like execution yet, it seems.
Yeah.
Okay, thank you.
Okay, thanks. Anything further?
Can I ask Anna a question?
Yes, sure.
So the compatibility that you mentioned, the definition, it kind of like sounded to me a lot like the edge regularity when you don't have directed graphs in the paper from Lauritsen.
Edge regularity.
Yeah, so edge regularity meant that two edges of the same color must have the same vertices of the same color. But for you, it matters the direction, so you just care only about the ending of them. And
Yeah.
the metrics then that you created, but that I did not get it well. I was hoping to see some vertex regularity there, something. Because you like the columns of your matrix that you created, Y, they like corresponded to each vertex of the same color. And somehow there is a notion of vertex regularity there, but it's not, I did not see it. I was hoping to see something, but also your interpretation, your wording was very different, so I could not match them, or at least to interpret them. But
Yes.
it seems like a similar story, but for the directed graphs.
That's right, yeah. I mean, essentially, that's the whole paper. It's a similar story to the undirected case, but sort of seeing how it all extends to the directed setting. So one difference, as you say, is for the compatibility condition, you have your two parent vertices and your two edges and your two child vertices. You don't care about the, there's no condition on the colors of the parent vertices, just on the children. So that's one thing that that, as you said, that the directed setting gives you. And we didn't also another, so we were looking at maximum likelihood thresholds, so how many samples you need for the MLE to exist and to exist uniquely. And there we had some extra condition which did involve the vertices, which I didn't mention in my talk, which is that there can be no edges connecting vertices of the same color. So you can't have like blue edge, blue. And this assumption we think we can get around, whereas the other one seems a more challenging obstacle. And also it was only needed in certain results, whereas the compatibility we really needed like all throughout the paper. But that's one place where a condition on the vertices did show up.
Anna,
I don't know if that answered your question, Aida, and I'd be really
Yeah,
happy to talk
yeah,
more.
thank you.
Anna, sorry, Jane, please.
Yeah.
Please, Jane.
Also for Anna now. So did you think at all about like, so in that same paper, they had these RCOP models, and Aida and I are thinking about these right now, so that's why they're on the brain.
Okay, fine.
So I was just wondering if you thought about if these kind of extending what you've done to those, and when your coloring is generated by some kind of like permutation group, automorphism group.
Yeah. So as far as I can tell, but I may be wrong, certain colorings will be given by permutation, so some kind of exchangeability between a subset of the nodes, and some won't. But then, so I suppose the question is then, do any of our results, can we strengthen any of our results in the special case where it is induced by permutation? And we haven't thought too much about this, but I would guess probably yes. So we have these maximum likelihood thresholds, which we're not able to find just to give ranges for. So we have a range for existence that depends on the coloring of the graph, and a range for uniqueness that depends on the coloring of the graph as well. So just on this sort of combinatorial input. And I would guess that in the case where the coloring comes from some permutation, that would be the sort of natural class of models to look at to try to resolve these bounds and turn them into actual thresholds. So yeah.
And Anna, in these thresholds, the bounded threshold is the same as the uniqueness threshold, right? Is this correct?
That's right. Yeah. So we always have that the boundedness is the same as existence. And then interestingly, our bounds sort of look like this. So we have an existence range and then a uniqueness range, and the upper bound of the existence one is like very close, or maybe even the same as the lower bound of the uniqueness one. So they like sit side by side.
Okay.
Yeah. And then in the case where all the colors are different, you obtain the upper bound of the existence one and the lower bound of the uniqueness one, because
that's the case, and that one knows.
Right, exactly. If you don't have any colors, or if all the colors are distinct, then the threshold for existence and uniqueness is the same.
Nice.
May I just ask also a few questions? We're at the end, but it's an open debate. Firstly, for Anna, in terms of DAGs, is this applicable to general DAGs I mean, DAGs are naturally of a lot of variety. Is this applicable to any causal graphical model in this sense? And also just two very short, more general ones. You mentioned during the talk, I think it was Aida, Brownian motion trees. Two concepts from probability, could they be applied to algebraic models? Could this be somehow merged together? Because Brownian motion trees is a discrete model, if I understood correctly, or on the boundary of discrete and continuous, but could concepts from probability also be like Brownian motion and so on applied here? And finally, just a very short one, when we discuss this ML estimation, would concepts of parametric and non-parametric estimation make any sense? Could non-parametric estimation be applied in a rational MLE estimation? Thanks. 3 questions. Yes, I hope we will manage on time. You have enough.
Yes, so maybe I'll respond to your first question, which
Thanks.
was, I think you were asking, if I understand correctly, I was talking about starting with a DAG model with Gaussian random variables and this independent noise terms, and then introducing colors into that and sort of seeing how that affects maximum likelihood estimation for those models. In principle, one could do this for any DAG model, so it need not be Gaussian, or you could consider the case where the noise, the error terms are no longer independent, and introduce colors there and see how that influences the thresholds for existence or uniqueness of the MLE, or how to compute it, and so on. So I think those are all interesting future directions to pursue. And I suppose in this setting where you have dependent errors, then that introduces bidirected edges into the model. So perhaps one could consider also introducing colors on those bidirected edges. So yes, I think there's lots still left to do along those lines.
Do the general conditions that are applied in graphical models like orthogonality, excludability, and so on pose any problems in your estimation?
What do you mean by excludability?
Like usually you have these conditions, the do calculus that is applied in graphical models on relationships between the variables, some conditional independence, and so on.
Yes. So exactly. So these models don't introduce more conditional independence into the model. So I guess that also touches on your parametric versus non-parametric question. So that's sort of benefit rather than a problem, because maybe you don't want to impose too much conditional independence between all of your nodes. So the set of conditional independence relations will still be the same, but you're restricting the model in a parametric way. Yeah, thanks a lot for the question.
Thanks.
Maybe I continue.
Thanks.
So I hope I did not understand the question wrong, but if I'm not answering your question, please let me know. So the Brownian motion tree models, they are not discrete, like they come from a probability, and they are a name for when you decide when you are assuming that the species have Gaussian distribution. So that's just a multivariate Gaussian distribution with the name Brownian motion tree model. And the connection with the discrete was just because on their own, Brownian motion tree, the space of covariance matrices of Brownian motion tree models is a linear space. But the inverse, which is the space of concentration matrices, that ended up being a toric variety, which was proven by Piotr and Bernd and Caroline. And so, and what we did was like we connected the model that they proved, like the toric variety that they proved, we connected with the phylogenetic model, which is discrete. So that's how the discrete entered into the game. But on their own, they are not discretes. It was surprising that they had connections with, close connections with discrete case.
Thanks, but just to add, is it possible, a more general question, to connect probability type reasoning, one could say calculus, which is based usually on analysis, and algebraic modeling perspectives, algebraic statistical perspectives?
I'll say what I'm thinking for the moment. Like in my sense, algebraic statistics is not really algebra and statistics. It's like we use whatever it works. So whatever it works is very welcomed, and analysis is very welcomed. But and I would assume other people have used analysis more than me. So if not, yeah, analysis is very welcome, and probability more is very welcome.
Okay, thanks. Okay, thanks. We're way over time, I would say. If there is no further question, thank you to naturally all the speakers, the excellent discussion that we had, to the questions from the audience. The webinar was recorded. It was also live streamed. I kept to check what happened and so on. So it will be accessible on the YoungStatS YouTube channel, visible to everybody in the next days. Thanks again to all, and hoping to see you on another statistical, I would say, opportunity very soon. Thank you. Thanks to all.
Thank you very much, Andrew.
Thanks a lot, everyone. Yeah, thank
Bye.
you.
Thank you very much. Yeah, bye.
Thank you very much.
Bye.
See you.
By the way,